There we go. All right. Welcome, everybody. And machine learning session. So, and we're going to go over our project update from Tony and the team at SFEI. So take it away.
Well, I guess, Walter, just to kind of step forward in with the order that we have, we might want to cover some of these things first before we do the project update. What do you think?
Sure, definitely.
Okay.
Okay. You want me to dive in?
Sure. Yeah.
Okay. Sure. Yeah. So welcome everybody. And as described in the in the summary and intro, I think we see that obviously AI and machine learning are quite ubiquitous out there in just kind of the way we use it and consumers and all of that. And then I think there's a lot of industry adoption across, it's part of the whole digitization movement, right? The same way, it kind of began with, migrating things from kind of manual into the digital world. And then, now we see it going into industry specific areas. And so, I think it's been taking hold more and more especially with litter. I think in a way it's unique because litter touches on water quality and there is some automation in water quality, but because I think the litter catches the kind of the public eye and public awareness, I think there's probably more interest in pulling in, like we talked about, like the Google demo and the platform they're working on. I think it brings in other stakeholders into this space that then bring the technology with them, right? So, Google's developing their litter platform as a part of their entire, so there's a sustainability insights initiative or platform that they have. And so litter is just basically a subset of it. So I think it brings that along with it. And so I think one of the more specific cases, there's, of course, and we'll talk more about the AI applications and the projects and things like that later on. However, basically there's kind of the conventional machine learning, the stuff you do with like tabular data. You could do spatial analytics with it. But I think more recently, one of the things that's really caught on is the computer vision aspect. In particular, anytime that, in order to pick up trash, we have to first identify it, right? So, everything from beach cleanups to basically the ocean debris to things that we're working on, both, SFEI and also CalTrans, trying to identify litter, whether it's on streets, whether it's in a wetlands, whether it's on our highways. I think the repetitive task of, being able to identify like visually, and obviously we at CalTrans have the visual assessment requirements for the State Water Board, among all other, permittees. So I think this is a really good opportunity to leverage that. And so I know that we've done some work with doing some pilots, even before Google, and also seeing what industry is doing. So there's been a lot of studies using drones, sweepers, LiDAR, ride sharing cameras. I know, Tony, you and I talked about it. So I think there's a wide number of leveraging these, in a way, kind of big data, right? It's kind of cliche, but leveraging big data. All these data sources are coming from edge devices, basically, right? All these little cameras that we see, on vehicles and things like that we'd like to leverage. So that's, again, something that's evolving and something that I think can help us with that automation to get, these assessments. And then also, once we have it digitized, then be able to do the mapping, the geospatial, and the reporting, and all the other things that we'd like to do. And really, in the end, help with the litter problem, because we can really shorten up that feedback cycle, right? We go out, we do assessments, we know where the areas are bad, we can put things on a map, kind of like Gary Conley and his company, and the company he works for, Second Nature, being able to put things on a map and then help permittees and also just citizens, right? Apps like Literati, where, you can take photos and it gets crowdsourced, you can see it show up on a map. So it really shorts up that feedback loop, and then really either deploy forces or, in the case of Literati, make it back to the producer of these products, being able to get that, and then really in the end get us to removing that litter more quickly. So again, in this group, or in today's session, again, we'll be having more of a discussion, going over the overview of these applications, and then in the afternoon, we'll come back after the Google demo. We'll be doing some hands-on projects. Again, that first one being the computer vision. It's going to be written in Python using the Tensorflow library. and then some other ones as well, because Tony and I partnered on a similar session earlier this year. So a little bit, something for everybody as far as, being more hands-on. And then again, it's all to share, and you all can, basically clone these and then work with them. And then again, we'll be working on those examples. So maybe Tony, I'll pause for feedback questions.
Yeah. I just want to put the button, just kind of a button on one particular point. One of the things we often hear is that assessing trash, being able to detect trash, being able to figure out how much trash is in our environment, and is it changing for the better or worse, that those problems are really challenging because trash is ubiquitous. You think back to what Charlie Moore was saying, just about how big the problem is. And it's going to take really huge thinking and revolutionary thinking. And one of the opportunities we see with the use of these tools, artificial intelligence, machine learning, is scalability, right? That's something that it really is strong at doing, is being able to scale up, where if you tried to just do the usual thing, that is hire this person to go out and look at things manually, it just doesn't compute. You just can't get enough scale to put your arms, your mind around the problem. So that's one of the things that artificial intelligence is particularly good at, is scale, because then it's just a purely geometric line where you can apply money and be able to scale up, and in some cases more than geometric, but exponential, as things become more and more efficient. So that's really what we're looking at. Do you have any questions for us just right off the bat about the nature of what we'll be talking about today? And you should be able to take yourself off mute if you wanted just to talk up. We don't have to raise hands here. Hearing none, we'll go ahead and proceed.
All right. Yeah, I'll continue on with the slides here. So, at the beginning, at the start, obviously, we'll just do, I think, get a sense of, areas of interest, maybe something as far as AI or machine learning, maybe everybody just wants to learn more, and we're happy to just, continue down that path, or is there areas of focus? And then also maybe what you see in your particular niche, probably be good to know, might help with this discussion and kind of the way we take these projects. I will add too to the last slide too, is that one of the key things that we, that I guess I have observed, and also some of the feedback that we've gotten, is maybe twofold, which is, the barrier to entry, right? And I think there's been a lot of advances as far as using machine learning for these tools. The things we're going to look at today are probably more on the technical side. However, things like literati, there's, many more apps, also the Google Liter Insights demo. And I think that's a good segue, where the other piece of feedback we've received is, well, how do we make these tools more accessible, beyond just a barrier to entry? If you're just, say, if you don't know how to program, or you're not very technical, how do you actually leverage these tools? So that's the one demo. That's why we want to have, we're partnering with Google, both for our use, but also for stakeholders. So one of the things we'd like to do with that, they're going to basically present a prototype, but that would basically be a consumer-facing app, and then it would be open for municipalities, stakeholders, and others to actually be able to look at the trash levels in their areas. Think of it like in a way, an open source version of a tool like Second Nature, where you can actually look at street view, based on their imagery, to look at trash levels. And again, working on, these tools are starting to evolve and become more mainstream. So I think we're getting there, whereas like 5-10 years ago, this was all fringe stuff, right? But I think we're working on that. And I know when we initially did our pilot at CalTrans, that was a lot of the feedback, right? We did a pilot that was more internal, but now I think we're doing these partnerships where we can hopefully, make these tools more available, as well as sharing all these best practices that we're learning. Part number 2 there, yeah, I think the use cases we're starting to talk about, but then also talk about the existing tools and frameworks. I think that'll also segue us into the projects. Part number 3 is definitely the hands-on lab. So as mentioned, we have the computer vision, as well as some tabular data sets, and also some good open data sets for folks to look at. And then to round things out, probably today or tomorrow, be able to summarize our findings and be able to report out, especially around demos or being able to work with these projects. So next slide, please. All right. So there you go. So I think, as we're going through, just, as Tony and I love to, kind of continue on with machine learning, I think it'd be good to just have a quick check-in with, just get a sense of, all the attendees. Maybe, we could just go through, just a brief intro, maybe, name, organization, maybe area of interest, and then we can go from there. And then, so, I'm Walter Yu, Clean California program with CalTrans. So we're Clean California is a, basically a litter abatement program, all, quite large. It's actually $1 billion allocated from the governor's office. We're actually pushing really hard these days with litter cleanup, adopt the highway. We're doing a lot of cleanups along the side of the road. You may have seen us out there. We have a public education campaign we're rolling out. We're doing a lot of partnerships. We're offering, free dump days, all sorts of stuff out there. So this will be going for the next 3 years. We're also including some beautification projects, local grant projects. So that's kind of my role. Prior to that, I worked in our environmental division and then got in touch with the State Water Board and all the great folks here. My area of interest is computer vision, machine learning, statistical analysis, all that fun data science stuff to help remove litter, help the litter problem in California. With that, I don't know, Tony, have you already done intro, and then maybe we just go down the list there of attendees?
Sure, yeah. So as I mentioned, so I'm Tony Hale with the San Francisco Estuary Institute and program director for environmental informatics there. So that basically means I'm the head tech guy. And among the things we've done is to do a study that you can find at trashmonitoring.org that helps to enumerate some of the more commonly used trash assessment methods. So I invite you to take a look at that. But for today, it's mostly going to be, as I said just before Walter joined, Walter's Batman and I'm Robin. So I'll be kind of sitting shotgun for a lot of this day. So Bob, do you want to go ahead and introduce yourself?
Sure. First of all, if you see me standing sideways, it's because I have two screens and you're on one and my camera's on the other. But I'm definitely attentive here. I'm the founder and co-owner of Carnegie, or that was an old company, Mobius Intelligent Systems. And we're currently working on a DWR grant, working on GIS systems and collecting data related to trash going into storm drains and streams and that sort of thing. I work with the regional watershed groups, the American Basin Watersheds Council, and we're setting up a shared information platform that'll be free to the public and everybody will be contributing data called watersheds.net. That's just a free public platform. It's not a for-profit project. And then we also, within the last 3 weeks, picked up contracts with about 40 California cities doing AB 1383 auditing. And we have a GIS system set up and auditors out in the field, I think, I don't know how many we're up to now, but working with consultants that have those teams in the field. And we're collecting GIS data and taking pictures of all these bins and assessing contamination rates, specifically related to organics, but collecting other things as well. And we want to start getting more systems into place where we can visually identify some of that litter or what's in these bins as contaminants, rather than having people just enter it all in, because we're going to be doing hundreds of thousands of audits in locations. And I'm also working with local water groups and that is supporting the DWR and with identifying what types of crops are growing on land, different pieces of land, using the NAPE database. And we want to, there's a lot of it that's out of date where it'll say it's eucalyptus when actually it's soybeans now. And that determines about how much water they use. So we want to implement a system that will help us visually identify those from the NAPE imagery and be able to determine what the current crops are there. And those are my areas of interest right now.
Great. Well, thank you, Bob. I see Darcy on my list. Darcy, do you want to introduce yourself?
Sure. My name is Darcy Gatilla, and I do environmental consulting with Althouse and Mead in Paso Robles, California. And I work on several construction sites, and the unhoused community has moved in once the infrastructure has gotten developed. And I think on one of my sites, there's like 8 encampments, and just watching. That's one component, and just I don't know, I'm affected by it at a level probably greater than most of people that are do any monitoring work. And so I just want to be part of the solution, and just want to know what's going on around the state and see how I can offer support.
Great. Well, welcome.
Thank you.
Eric, can you introduce yourself, please?
Yes, hi, my name is Eric Garcia. I'm a consulting hydrogeologist here in Sacramento. My background is in high resolution site characterization technologies. Did some training in machine learning over the COVID period, and found that this might be an interesting use of my expertise.
Excellent. My colleague Lorenzo Flores is here. Lorenzo, do you want to introduce yourself?
Sure, yeah. My name's Lorenzo Flores. I'm a software engineer here at SFEI. And I was working alongside Tony on some of the machine learning stuff we did here at SFEI. So yeah, it's a pleasure to be here, and I'm excited to see what conversations develop.
Thank you, Lorenzo. Ying, can you introduce yourself, please?
Hey, my name is Ying Jin. I'm a professor at SexDay, Computer Science Department. My research interests are database systems, active rules, and data science. Thank you.
Good to see you again, Professor.
Good to see you again.
Yes. Fawn from Literati, can you introduce yourself, please?
Sure thing. Hi, everybody. So my name is Fawn, and I am from Literati. My role here is the City Success Coordinator. So I work with cities around the world, helping the cities you have their residents use the app, really get people involved to drive change. I am honestly not the most techie person at Literati, but if you have any techie questions, I am happy to forward your question to our tech team and make that connection. So excited to be here.
Great to have you. Let's see. So Ali, I see you there. Can you introduce yourself, please?
Yeah. Hi, everyone. My name is Ali. I work for the San Francisco Regional Water Quality Control Board. I'm an engineer, and I work in the stormwater program, the Municipal Regional Stormwater Permit. I work on the C10 provision, and I'm interested in learning more about machine learning, about the use of drones in quantifying trash in receiving waters. And it's good to be here.
Great to have you here, Ali. And it's good that we have our names underneath, because I look at Ali and I kind of get him mixed up with me. So I'm glad that we're able to tell ourselves apart. Should I go ahead and move to the next slide, Walter?
Yeah, definitely sounds good. So with that, yeah, I think, yeah, thanks for the interest, everyone, and sounds like we have a pretty good mix. I think that, yeah, I think there's a variety of interests. I think most in general, everybody's interested in machine learning. Sounds like maybe for a couple of folks, maybe how it all fits in with what you're working on now. I think keeping in mind that machine learning, there's a wide variety of use cases and applications. I know I got started more on the tabular side, actually analyzing data, but again, it's gone beyond that. Esri has a lot of spatial analytical tools these days. They're actually integrating with computer vision in the parts of what they do. And then definitely in the computer vision space, I think a lot of consumer facing apps. We chose at least for this group project to do for today, Tensorflow, because it's open source. You can really dive in to see what you're doing. However, Google Cloud, Amazon, Microsoft, they all have basically more consumer-facing apps where you can basically upload photos and train them, and then you don't really have to do much more than that, right? You just kind of create the labels, you can draw your bounding boxes. So our initial prototype at CalTrans was actually using Microsoft Custom Vision. So, it's evolved from that since then, but there's a wide variety of use cases. I guess maybe this is more just like an open-ended. I think we got a sense of everybody kind of talking about what they do, but maybe if anybody wants to kind of, just give a brief blurb or summary of maybe things that you see. How's the state of AI and ML within things that you're working on? Maybe things that you see. I'll open it up to the group, and feel free to chime in. Or maybe is it that maybe, let's put it this way, would it be that, is it you all are curious about to learn more and what Tony and I have as far as, kind of what we have going on, maybe for ideas of how you could bring it back? Would that maybe be more the case?
Well,
Mm-hmm.
oh, go ahead.
You go ahead, Darcy, please.
I was just, I guess wanting to know what tools are available, and then bringing that, at a county and a city level in San Luis Obispo County. I don't know I know the cities are grappling with these issues. And so just curious, what tools they are currently working with, and then, kind of bringing this back to them.
Definitely. Yeah, that sounds, that's a good one. And then, go ahead, Bob.
Yeah, I'm finding more and more as we do this work, I'm finding other people that are working on similar projects or projects adjacent to where we are. For example, I'm already working with the RMDZ Recycling Market Development Zones in San Luis Obispo, and I've never heard of Darcy's work or what she's doing, and I should have. And so anyway, I'm finding all these silos. And I think if a lot of us can connect, data and big data, the more better data you have, and the better it's cleaned and all of that, sanitized and put together and structured well, we can create consistency across some of these data lakes and be able to do more together to get better end results. And, I might be working on one project and Second Nature on another and doing the same kind of work, but we're really all on the same team. We all want to accomplish the same thing. And so the more we can collaborate and get some consistencies and standardization across data formats and just learn about what each other are working on, I think the more we can really take that on and, get more exponentially working together than we could individually. So I'd like to learn more about other people and see how I might be able to support or get them with support for me, So that's what I'm here for.
That's really great to hear, Bob, because I think it meshes well with both kind of what Walter and I work on, and then also a lot of the opportunities that we're focusing on as ways to increase collaboration. So that's fantastic. And I know that others have more thoughts on this, but I just want to make sure that we don't lose the opportunity to introduce some newcomers here and welcome them. So Denise and Janet, I see you there, and then there may be another person as well. So Denise, can you just introduce yourself by way of your affiliation and your interest in artificial intelligence, please?
Sure. Can you see me?
Yes, we see you great.
Okay, cool. So yeah, my name is Denise Brown. I'm a founder and principal of All About Waste. It's a small sustainability and zero waste consulting company located in California. I am very excited to be here and with you guys. It seems like you are all experts in waste. I've been working with waste for a long time as well. But my main focus and my clients are normally like commercial buildings and facilities. So one of my interests about learning machines, and I know there are a few, maybe one or two companies in the US that can provide actually like smart bins. So how can we basically reduce contamination, basically
where we generate the waste. So in offices and meeting rooms and pantries and kitchens and so on. So I am very interested in learning more about the technology that we can put in buildings, and could be all the way from a tech company that we work with, that they have offices all over the world, all the way to airports and train stations and so on. So that's my main interest. Thank you.
Thank you, Denise. It's great to just see the wealth of imagination that everybody's bringing to the table. And so many of these things are possible now with the kinds of information technology we have. So Janet, wanted to turn over the table to you for a second. Yeah, thank you, Denise. Janet, would you please introduce yourself and your interest in this technology? Maybe Janet stepped away. If there's someone else at the 909 number there, if you want to take yourself off mute if you can, and I think it's up.
You're unmuted here. You have to talk here.
Yeah.
Yes, we hear you now, Janet.
I'm sorry. I'm trying to do this from the phone because we are leaving. Anyways, so my name is Janet Rodriguez Lipsy. I was a county employee. Hold on, because now I have the phone and the computer, so I'm sure you are hearing an echo. Give me 1 second. Okay, can you hear me now?
We hear you fine. Go ahead, Janet.
Okay, so I left the county to do my own consulting business, mainly with stormwater, involving stormwater runoff. But the reason why I wanted to join you is because while at the county, we use as a BMP for trash control, the street sweeping. So I just was wondering how you guys could merge this high technology approach to something that is rather, I don't know how to put a name on it, but it's a street sweeping, because a street sweeping really controls at the source. So seriously, I am here more like a learner and see how I can somehow put these two things together, this very high technology with a technology that has been there for, for forever, street sweeping. That's pretty much why I'm here.
Yeah, thank you, Janet. We will be actually talking a little bit about street sweeping coming up in a few minutes. So hopefully
awesome.
that nexus works for you. So thank you. The questions we had to the rest of the group for this group discussion was, how would you use AI within your organization? What do you see as the opportunities and challenges? We heard from, I think, Fawn, it looked like you were poised to chime in there. Did you have something to add?
No, nothing to add right now.
Okay, that's fine.
Yeah, definitely looking to collaborate though and help out where we can.
Excellent. All right, so do we want to keep on this, Walter, or move to the next?
Yeah, no, thanks everybody for your feedback, and good to note. I think, yeah, trying to keep in mind, the different use cases and, I guess entry levels. But yeah, we can continue on with the next slide. Yeah, so continuing onwards. Okay, I think that's over to you, right, Tony?
That's right, that's right. So what I'll be talking about here is some work that we've done through the project that you'll see detailed on trashmonitoring.org, all one word, trashmonitoring.org. And there you'll find a field testing report as well as a trash monitoring playbook. But then we go a little bit further. So this is an opportunity to share some of that, and then also some updates that we've done through our work with the California Department of Public Health. And when I say our, I am referring specifically to the San Francisco Estuary Institute and our collaborator, the Southern California Coastal Water Research Project. So those of you in Southern California are probably familiar with SQUIRT. All right, so computer vision, that is really focusing on, so Walter mentioned that he got to start working on tabular. This is about looking at imagery imagery or video of some sort to detect things typically or interpret the imagery. In the case of trash, it really is how do we use computer vision to help us detect and measure trash? That was a question that we had. So among the things we wanted to do is to pair computer vision, the artificial intelligence, with unoccupied aerial systems, drones, right? Because we were talking earlier about the problem of scale. And if you're able to fly, you're able to get out of what you're locked in at that terrestrial zone, and you're able to get up and see a whole lot more with fewer resources. So we did this experiment. I'm going to kind of like hustle through some of this. So if you want me to go into greater detail, I'll stop. But I just want to point out that Lorenzo Flores, who's here, he was part of all of this, and he was the main software engineer behind the artificial intelligence, and he worked alongside Pete Kohanen, who was the drone pilot, as well as Rylan Hunt of the Kayaks, who volunteered his time to work with us and further extend our efforts. So we flew these quadrats at various altitudes, 30, 60, 100, and did some ground truthing just to see kind of like what we could see from different altitudes. And the reason why that's so important is because the higher you can fly, the more ground you can cover, but also the higher you fly, the lower the resolution of your imagery, right? You're seeing things from farther away, so fewer pixels per object. And among the things we found is that with our off-the-shelf, now you talk about kind of like what's feasible, we were flying just a cheap drone with delivered optics. So we weren't using any sort of magic here. We were using readily available commercial products. And we found using those products that about 60 feet is where you saw some drop off, particularly with tobacco trash. And I'll be focusing on tobacco related trash for a lot of this. But you can see that there's, the ground survey is able to achieve counts of so much. And then there is a drop off of the total once you get to 30 feet, once you lift off the ground. And but there's a pretty good match between 30 feet and 60 feet. And then it starts to go a little bit down further. So 60 feet was kind of that magic number where we're high enough to cover ground, but we're not so high that things become blurry and indistinguishable. So some of the goals we had for tobacco product waste assessments would be to expand that geospatial range, to increase temporal density. That is, if you can be a lot more efficient, then you can get out a lot more often, because as you all know, trash is so changeable. It comes with the wind, rain. We've got these storms, so trash that's higher in the watershed comes down and moves around. So increasing the temporal density can give you a more realistic picture of where things are. Enhancing the ease of data collection. So instead of a lot of work associated with this, if we could make it easy for people, the better off we are. And then to automate the counting so that you're not just kind of like taking imagery and then counting manually, but you can automate that and improve repeatability. So rather than having things vary among assessments and among assessors, to make it more consistent. And this speaks to what Bob was talking about in terms of having standards. Certainly not so much about the data standards, but having standards for counting so that we're counting the same thing in the same way. And we fly above the ground so that we can maximize the area covered. We leverage flight planning software so that we can have repeatable assessments. You can fly in the same area in the same way at the same altitude to make things as harmonious as possible. Some constraints to bear in mind if you wanted to undertake this yourself is that it's according to current FAA rules, you need to maintain line of sight with your vehicle. You need to avoid obstacles, trees, telephone poles. That's obvious, right? But you can't fly over people that are not part of your flight team. So think about it. If you're flying over, let's say, a creek or river, and you're flying over an encampment, you got to avoid that. You don't want to do that unless they've given explicit permission. You also can't fly near airports. So in the Bay Area, where we have a lot of airports and exclusion zones, it means that there are only a certain number of places we can fly if you want to get down to the mouth of those creeks before they enter into the bay. Flying in heavily wooded areas is difficult because you can't see under trees. You also can't fly in inclement conditions, heavy fog, and rain, of course. We also highly, highly recommend that you get a FAA licensed drone pilot to fly. It's now feasible to get that license without having to, fly an actual helicopter. So it's possible to pursue that. So the automation of cigarette butts, and Fawn could say a lot about this because of her association with literati. This saves time and effort in performing visual surveys. We often hear that it's really time consuming for people to get out there and then count how many cigarette butts, which is the current practice in a lot of areas where you say 1, 2, 3, 4. Wouldn't it be great if you take an image and then you automatically count those cigarette butts? So for our method, what we did is we compared human annotations to machine learning based detections. And when under ideal conditions, we could see 1,008 cigarette butts out of 1,021. That's a success rate of 98%. So again, that's ideal conditions. Those would be flying at consistent altitude and flying over consistent background. In this case, we use Blacktop, as you see in this image. So we also seeded the environment so that we knew exactly how many cigarettes were in the environment. Seeding meaning we actually put them out there and then recollected them. So don't think that we were littering. We recollected all the stuff we put out there. Some details. So Walter mentioned TensorFlow. We were using TensorFlow 1.13.1. That's important. That's now out of date, but that's where we started. We've since upgraded to 2.x TensorFlow. And so you can see the different pieces that went in here. And Walter, we're okay sharing this slide deck with people, right? Walter's working on stuff. So we're going to share this with you. We can share all the details because what we really want you to do is to be able to emulate things that we did. And we can share, in fact, we can share with you this TensorFlow instance, and you can download the model as well as all the data associated with this work. So as far as the expansion, last time we provided updates, last time I'm talking about earlier in the year, so Walter mentioned that we collaborated on this before. So earlier in the year, we got up to this point, but then Akayak jumped in and said, what can we do to help you? And we said, well, we'd like to update to version 2 of TensorFlow. And we'd also like to see how the machine learning works with street sweeper-based imagery. So Janet, I'm looking at you now, as well as mobile phone-based imagery. So how can it work? Does it work just as well if you're kind of up close instead of operating at 60 feet? And also if you're in highly confounding backgrounds. So instead of just asphalt, you have all the backgrounds that if you were to use a mobile phone or a street sweeper where it's really complicated. So faster RCNN is you have this convolutional layer that creates a feature map of the image. And first, the regional proposal network identifies regions within the image that contain objects. And then you kind of zoom in, so the region of interest pooling extracts features from the image. So this is a little bit of a detailed view of kind of how the CNN, the convolutional neural network, does its computer vision work to kind of go in there and extract information as objects. So some of the parameters here, we converted TensorFlow from 1.13 to 2.3, as I mentioned. We made updates to the API. We also cropped imagery. And the reason why we include some of these details is that if you want to walk in our footsteps, it's really important to understand some of the constraints for what you're dealing with. There are only certain sizes of images that could be used for training, in particular for training. So we cropped those imagery to help with the training, and we did various steps along the way. So this is highly detailed. Again, we can give this to you afterwards, but the bottom line is that using, so the Blacktop, again, this is the ideal where you're able to get a high level of recall. The number one is like 100%, so 94% is what you see for recall. Street sweeper imagery, so picture the imagery, and I'll show you some samples of what that looks like, where it's like leaves and dirt, and we were still able to pull out about half the time, correctly pulling out cigarette butts from just images that were taken on a routine basis as street sweepers went along their route. And then for cell phones, we were able to get up to 60% recall, which is a pretty awesome figure, really, when it comes down to zero effort other than just shooting images. So this is an example of the Blacktop, right? So you see the consistent background. It was highly successful in pulling cigarette butts off of this. So you can see examples. Now this is a street sweeper. It's a little blurry. You have leaves, and we were still able to pull out a number of the different cigarette butts. So when you think about the effort involved, it's not a lot of effort, and you can get data out of it. It's pretty incredible, really. Again, here you see the leaves pushed together with all the cigarette butts, and it was able to extract that form, that special form for cigarette butt. And you see it here as well, the street sweeper. So just going through, and then we wanted to also see what it's like using cell phone on, let's say, sand, right? So you see a lot of cigarette butts on beaches. Could you do it? And these are true detections. Those little red boxes are finding the cigarette butts. And again, this is looking down from a cell phone. So some of the technical considerations are listed here. You have the training where, you know, the max size, we found it about there, the pixels for the images. There are a lot more constraints around the training than about the detection. So training is about, you know, priming that algorithm to detect what you need it to detect. You're teaching it. And so you can only use a single GPU for that. You can, your batch size is tied to the number of GPUs, your space on disk. There's all these different constraints you need to bear in mind if you're going to do that training. But then for the inference, for the actual detection, then things open up. You can use much bigger images. You can anticipate a faster clip. Your images must be color is something we found out. And we were able to leverage a very powerful GPU server, and it goes much faster. So the next step for us is to operationalize the model, to take what we have and then to create an API that would allow practitioners in the field to, with their mobile device, go ahead and detect cigarette butts. This is not doing the full range of things that something like Literati would do, but this is highly specialized for tobacco product waste in particular. And that's what we focused on after doing our more general trash algorithm, which is again available through trashmonitoring.org. All right, so I'm going to pause my screen share and turn this over to Walter. Walter, I need to just step away for a quick sec. So if you're there to share your screen and continue the presentation, that would be great.
Yeah, definitely. Thanks, Tony. Yep, I will take it away. All right, let me go ahead and do a screen share here real quick. So I'll continue on with the slides. Let me go ahead and do that. Let's see, I'm sneaking ahead here to, all right. Picking up where Tony left off. Let's do a present. Or sorry, let me go ahead. There we go. Should all now. Where is the share? There we go. All right, you should all be able to see. There we go. Everyone see the screen okay? Okay, tell me if you do not.
No, it looks good.
Okay, perfect. Should be the slides. All right, so so this is a basic. I think we're just going to give an overview of you know, AI/ML. It sounds like many of you are already very familiar, but those of you maybe that you know you're seeing this for one of the first times, you know, or new at least at the beginning. So you know, machine learning and AI can be quite a lot to take on all at one time. So you know, the way this is basically a taxonomy of you know, the entire universe, if you will, right? Artificial intelligence can be pretty broad. You know, you think about the general AI out there, you know, things we see in the media, but then there's more specific use cases where you know, you can start to see it branch out into these areas. You know, I thought this was a pretty nice way to think about, you know, in a way, think about ways that maybe we could apply these specific skill, you know, applications of this general, you know, space of AI. So starting at the top here, so machine learning, as I described, these are more the working with tabular data. It could also lead into deep learning, you know, but prediction for sure. So that's probably one use case, and we do have a demo for that today. If folks are interested to do a little bit of prediction, where you're basically taking a data set and, you know, it's doing, you know, if you think of it like a fancy, very fancy regression on it, using a little bit of different techniques, so basically training and testing data. So you're going to take a data set, you know, teach the machine learning model, you know, a little bit about the data set, and then you give it the test. And again, this is a very kind of overall, you know, summary or a digest of the process, but basically then testing the data, and it would give you predictions. So that's very kind of classical machine learning, how you can apply it for data. And in this case, it might help with, and we've did a little bit of work at CalTrans around how do we actually analyze our maintenance data to do some predictions or forecasting? So, that's one way to think of it. Or another common use case would be like in the popular media around maybe trying to predict a particular, like say Netflix, that's an easy one, a recommendation engine, right? You're using data and you're making a forecast of what a user preference would be. Same thing, Amazon, right? All these recommendation engines are an application of, say, machine learning of how to use data to make predictions. The next would be natural language processing. So this is working specifically with text, whereas in machine learning, we would have, mostly numerical data. We might be analyzing trash data. In this case, NLP allows, very specific working with text. So in this case, if there's what they call a corpus of text. So it could be regulatory language or searching the web very quickly, right? If you have like thousands of documents, being able to comb. So at the time of COVID, when that first launched, there were a lot of kind of data challenges or data problems around actually how to know what's out there about the virus, right? So being able to comb through, a large number of documents, so that's one potential application. So if we're interested to say in microplastics or ocean debris, being able to search through a corpus, very quickly and searching through all those documents, that's one application. Also within a particular document, being able to parse it very effectively using NLP. It's also very good at manipulating text. So, I think in terms of machine learning, anytime there's like text or documents, probably think about NLP and ways to use that. And then speech, probably not so relevant here, but that's continuing to evolve. It's basically being able to analyze or tokenize our speech, take audio signals and then convert them into words. And then for analysis, there's a lot that goes into actual translation of speech. So, again, not so relevant here, but, it's part of this realm of AI and machine learning.
Well, there's a lot of people who do trash talking, but that's a different thing altogether.
There you go. So, and then there, in this bracket here, the expert systems, planning and schedule optimization, and robotics, these are probably more on the automation piece. We had that photo earlier of, a recycling center with the robotics. And I know that Cal Recycle and other organizations are interested in, using computer vision to help with so automation around, robotics or sorting, items and things like that. There's also in waste management facilities, there's a lot of interest. So that's where there's that combination of both computer vision and then the actual automation as in robotics. So again, that's an evolving field. And there is starting to be more research and projects in this space. There's also a lot of like the DIY, the little like trash robots that go on. And again, you're bringing together machine learning, sensing, remote sensing together with robotics and actually doing something in the real world. So again, these are starting to be evolved. And then finally, the bottom there is obviously the computer vision, right? So there's the actual, and really computer vision, at least for litter, is really a twofold problem. And I can also give a brief demo of a project that we did, and we presented it at Casca in 2020. But basically, it's a two-level problem of doing identifying the object of trash and then actually classifying. So in a photo, if we're able to pick out how many pieces of trash there are, then we can get to the place of how, based on the number of pieces of trash, then we can identify, okay, how many, how dirty is this area. So that kind of combined and kind of like what Tony presented earlier as well, right? Being able to pick out the cigarette butts and identify how many there are, and then come to a conclusion or classification of how dirty this area is. And then that's how this would get combined with the visual assessments that we were talking about. I'll pause. Any questions here so far as taxonomy or applications and use cases? All right, continuing onwards. Not gonna, we'll do a very brief overview here. Let's do this if it will work. Let's see, let me exit out of this and do the timeline real quick. Again, I thought this was a pretty fun interactive, again, for probably, the folks that are newer to this space. Let me go ahead and share out. Quick, it looks like, okay, I'm gonna send out to all here within this group. Here we go. So put the timeline in the chat. That's the thing that we're looking at. I thought it was a pretty fun interactive. So this is a organization known as Label Your Data, doing basically work in the space of being able to label images, basically creating these data sets that would be useful for machine learning, computer vision. And they basically give a very quick rundown of, well, the full kind of the history, started back probably in the 40s and 50s with the very early beginnings of machine learning, and then segueing obviously more into the recent examples. And then, you talk about data labeling, how to leverage it for machine learning. But yeah, it's, they started back in the 40s with a very, very early beginning. So when they literally were creating transistors and the beginning of computation, almost going back to the time of like Turing in the 40s and 50s as it evolved, and then getting into, the very basics. I think the very first one was like, what did they call it? It was like a neuron receptor. It was like basically a little like toggle on and off to do some very basic computation. That was the very beginning of machine learning. And then from there it evolved. So let's go down the timeline real quick. So it basically started also on a logical level. It wasn't, we didn't have the computation available then yet, but that's where a lot of machine learning came from, right? Was the precursor to the actual machine learning models and the actual machinery to support it was more the statistics around it, the mathematical models around it. So we knew there were descriptions, but just no way of implementing. So that was the very beginnings there. And then they talk about, it's just kind of more the conceptual, the logical. You can start to see now they're starting to develop games. Again, the very early beginnings, as you could see that the mainframes are pretty big. These are probably the magnetic tape decks to hold the data. So again, we're starting to evolve there as far as computation and the machinery goes, or computation, be able to do that. So this is where, this was actually one of the first, as transistors are coming into place, these are the actual hard devices. So this is probably in a computer museum somewhere. And just to make sure you all can see the screen, right? I'm not speaking to myself, right? Okay, you guys can see the slides. Okay, good. Done that before. They're starting to develop now that they actually have some transistors and things in place. I think work groups are starting to form. It's getting much more academic. You can actually start to see the diagrams here now of actual neural networks, right? So this is specific to AI and computer vision. And then they're starting to describe the beginnings of neural networks, how convolution works, how you get from one layer to the next. So again, these are pretty, so the perceptron, I think that's what I was thinking of. It's a perceptron of actually creating these models where you can actually start to perceive a little bit more and pass the data through these they call them neurons, right? They're basically layers of this model. And then again, quite a lot of computation and academic research being done. One of the, again, they're starting to evolve these algorithms, right? But what they call a nearest neighbor, or being able to do clustering, it starts to border a lot on information theory and processing of information. Again, more full-fledged. Again, more and more, evolution, and this is where we start to see the convolutional net, which Tony talked about as part of his drone imagery research. So they're starting to do so you can start to see some experiments around computer vision and robotics. So this was starting in 79. So, again, these are things that have been all kind of in progress. Now you start to see more of these formal frameworks now start to come up as they start to do more research. There's actual frameworks and academic studies and application within industry. Continuing on, these are just more examples of research and different major studies that they've done. In this case, now we can actually start to see really powerful and popular machine learning algorithms start to be developed. So things like SVNs, support vector machines, or in this case, the random forest. We actually have an example using random forest. So random forest, basically, it does a form of basically what they call ensemble methods, where you're taking a bunch of weak classifiers, if you will. So in this case, in this diagram, they're trying to discern these two clusters of data. So the way they do it is they kind of pass it through these weak classifiers, right? So basically taking a pass and saying, okay, where are all the blue dots in the image? So it parcels it out, and where are all the red dots in this image? And so it tries to do a split. And then based on that, it basically recurs down and then uses a combination of these weak classifiers to arrive at a score. And so that's kind of, again, a very brief overview of, there's much more to it. But, some of these very popular and powerful algorithms starting to come into, actual coming to realization starting in the 90s. You can start to see now they're starting to get into videos, the infamous or famous chess, right? We all probably all heard of Deep Blue, but starting to use, more consumer-facing applications. I think there was more as these algorithms came and the computation got more powerful. So obviously IBM developed Deep Blue, and then gearing it for games such as chess or Go or things like that. So again, that started in the 90s, and really I think to capture the popular imagination. 2000, this is probably more the modern age at this point. And then, definitely get into 2009 where the image net is actually still in use. So it's actually a huge repository of images for machine learning and computer vision. So there's more than one. There's one called COCO, or Common Everyday Objects. So these imagery taxonomies and database actually power a lot of computer vision because they enable for generalized learning. So they have these huge repositories of images, they're categorized by objects, and then that enables machine learning models to be trained and then specialized. So again, we'll have in the example in the demo today, we'll be showing off that where there's actually, we'll be taking a look at COCO and then actually how to develop, and there's common off-the-shelf models, which are going to be applied to the imagery. And then from there, we're able to specialize and fine tune the model for our use case. For those of you that don't know, another pioneer in AI is Andrew Ng. He helped develop Coursera actually, and he's also a pioneer. He was in one of the leads in AI with both at Baidu and Google. He teaches at Stanford and did a lot of pioneering work as far as computer vision and AI, and really on the deeper end of machine learning. So he's really famous in the machine learning world. You can start to see now they're starting to fine tune. There's so adversarial networks is in a way trying to be self-generative. So they're kind of building on V1 of machine learning, if you will, and doing more advanced research. This also gets into GAN and other things. So I don't know if you all have heard of OpenAI, but OpenAI is a pretty big initiative and company, and they actually do a lot of work in this space of to start to actually do some automation. I'm hoping to find, I'm trying to find projects here. So things like, I think this, things like this, where it's actually starting to be self-generative, and actually a lot of this is open source code, but basically where in this case, they're trying to generate music from existing music. So this is where it's getting into like auto-generative AI. So this is where it's pretty cutting edge, but getting to a place where we could generate text, we could generate images and video and so on and so forth. So OpenAI has been doing a lot of work, for better, for worse. I think there's a lot of those that predict like this could be the end, right? Where you have like the Terminator come up and Cybernet come up. But this is, self-generative, and OpenAI, they're doing a lot of work in this space. So just want to make everyone aware of that. And then, going back to continuing on with the timeline. Yep, you can start to see now they're starting to do that generation where DeepFace, there's actual generation of new images from existing ones. Again, better for worse, good or bad. Again, these are more the common use cases now these days. Google is starting to basically have major initiatives to deploy machine learning across all of their models and products. And so it's becoming, again, and this is happening in a lot of other industries and spaces. Again, I think these are just more consumer-facing applications, self-generated. We've probably all heard of Alphago, which we thought, many thought was an unsolvable game, or ones where, it wasn't like chess, right? The number of moves was just like orders of magnitude larger. So, well, they finally got around to it, to actually solving or winning at Alphago. So, you know, as they pointed out, they're able to actually beat a lot of the world's best players. So that was really good. This is where we actually have now starting to get these generative kind of scary stuff, right? Deepfakes and things like that. So, so it's going to be the technology starting to evolve. And then definitely more common use cases. So Waymo, right? Autonomous vehicles, again, more use cases of this. But keep in mind, this is actually leveraging computer vision, right? Because behind every autonomous vehicle, you'll see that there's these devices up at the top of the vehicle. There's a ton of sensing. So there's not only computer vision, there's LiDAR, there's a number of sensors. So in a way, these are basically becoming mobile computers, the number of technologies they have to have. And Tesla's not the only one. A lot of vehicle manufacturers, right? Toyota, Volkswagen, they're all you know, getting on board with these technologies. And behind them, again, the driver, both the hardware and then also the models that have to go behind it. So computer vision is actually a big driver, and it's also a lot of remote sensing. There's actually also a lot of conventional companies that are getting into this space, especially those that specialize in LiDAR. Actually, interesting story. One of the major players as far as LiDAR and sensing is Velodyne, and they actually used to make acoustic equipment of all things, but then they transitioned and they pivoted into AI. So I can show a screenshot real quick.
So yeah, while you're bringing that up, Walter, just to jump in to say that the Waymo model, where you have these you know, autonomous devices out there, it's a pretty good analog to some of Denise's suggestions about those kind of like smart bins, where you have these edge devices with embedded AI that might more or less operate autonomous of a net, you know, and be able to have some either data collection or decision-making capabilities. So when you're thinking about, Denise, the opportunities to embed smart devices, these kind of AI-driven devices into commercial buildings, you know, these models are kind of close in the same family.
Yeah, exactly. And yeah, this is Velodyne, and so they make that basically the pucks look like this, and they're the same ones that go on top of vehicles. And so there's a lot more consumer facing, where Velodyne, NVIDIA, there's these companies that were kind of in other fields, right? NVIDIA used to make video, they still do make video cards, right? But they got into the GPUs. But these advances in both the software and the hardware have enabled autonomous driving, autonomous vehicles. So yeah, that's it's pretty interesting how, you know, again, conventional companies have now pivoted and really made an impact on this space. And yeah, thanks for chiming in, Tony. Close these out. All right, I lost the slides here. Sorry, give me a moment here. I'm gonna have to backtrack here. All right, so I'm gonna have to scroll down here for a moment. We're almost to the end of this. Actually, we'll skip ahead. We're gonna go back to, we can time travel here, go to 2017. I think we're near the end here. Yep. So Waymo, and then data labeling. So that gets to, again, supporting the imagery that powers computer vision, machine learning. And then again, you know, if you're firing up on this link, you know, they do other things here on the site. But that's a very kind of, you know, from the very early beginnings in the 40s and 50s all the way to machine learning. And then I think they started pivoting once neural nets came into place, came into fruition. I think that's where it got, you know, much more interesting as far as applying it for imagery. And it applies also for, yeah, I think neural net, it's I think one of the better suited ones. So you could also use neural nets for, you know, analysis and other things like that. But one of the primary ones, and I think neural nets are also very good at what they call unstructured data. So whether it's audio, whether it's images, you know, things of that nature, it's really geared for that. Big data in the sense of not like a really large data set, but like if you have thousands or hundreds of thousands of images, or just really big files, which are again unstructured in that sense, it's very good at doing that. So very brief overview, very quick overview of the timeline there. And then I have another one here, just want to show this off real quick. Talking about AI and art, I'm not going to go all the way through this, but you could, I'm going to put this link in the chat, but I think you get a sense from the last one, but This is more another application, if you can think of it outside the box a little bit, but using AI to actually generate. So we might have heard about, and so it goes through the same thing, right? But actually how, you know, the beginnings of artificial intelligence, machine learning, and into current day of how you can actually apply, or how it impacts, as a positive impact on art. And again, thinking about things like we just talked about, right? The auto-generative, creating content, things like that. So a little different angle, if you will, and not just kind of in the litter space or consumer-facing space that, you know, people are leveraging artificial intelligence other ways besides, you know, the ones we just talked about. So let me just maybe hit on the highlights. Is there anything of, you know, they're starting, yeah, so the same thing, right? They're starting to talk about the beginning of the neuron, kind of machine thing. So again, starting to border into tiering and the general notion of artificial intelligence, you know, people's imagination. There was, I will note, the AI winter. So after the initial Perceptron, there was actually naysayers in the community, and I think it was a little early on. People got too excited, and then, you know, I think it got pulled back a little bit when they realized, like, hey, what are the actual use cases? So there was an AI winter where it kind of slowed down and then picked back up. You know, so again, evolving, yeah, it's the same photo that we had. You know, once we had computation and the actual, and in this case, it looked like they were actually playing already checkers with it, and beginning in the late 50s and 60s. You know, again, kind of seeping into popular media. You know, and then now we get into starting in the, you know, even in the 70s, being able to generate some imagery using, again, machine learning and AI. You know, and then again, starting to digitize. Yep. So AI winter. So they do reference that. But again, trying to think about some more mainstream or commercial uses. So, you know, that started to come on in the 70s and 80s. Yeah, continuing onwards. So again, more applications in, you know, chatbots starting to come into play. So that's another use case. Again, not so much for litter. Yeah, chess, there we go. We talked about that. Robots, right? Everybody's heard about the Roomba, things like that. So again, combination, and actually many of the DIY projects are like this, where it's both trash and then computer vision, and then you see the interface. And so again, limited, you know, broad use, but again, just an interesting application of where you're bringing together robotics, and then you're driving that with the software doing remote sensing. Again, more consumer-facing apps. ImageNet, yep, this is the same one to power imagery. And then again, more kind of common use cases. You know, yeah, and then you can actually now see where they're starting to use AI to actually generate. You know, there's like Deep Dream from Google and other ways to apply. So I think you guys get the point. I'll let you guys use, you know, I'll let you guys kind of look. Yep. So there's Deep Dream. So I'll let you guys kind of look at this just out of general interest and fun. Yeah. So making, you know, art, generating paintings. So I guess that begs the question is, you know, will it actually replace artists? Will it replace other people who've actually had these jobs? I think in many industries, it'll actually supplement, you know, like we've all heard about different use cases like autonomous vehicles or robo-advisors, right? Are they actually going to replace people? But I think the reality would probably be a combination of the two, right? Where people will actually leverage machine learning. But that's just one hypothesis, right? We all don't know what the future would hold. Yeah.
Yeah, and something I think about is the types of things that we are targeting are things that just aren't happening because they're just so arduous for people to do that no one is really doing it. People aren't out there counting how many cigarette butts there are. People aren't out there surveying how much trash there is in a storm in a MS4 system. So, you know, there's just so many things that are not happening because it's just not really feasible to pay anyone to do. So those are the types of things that can be targeted. One of the takeaways from what Walter's been presenting that kind of strikes me is that, first of all, the history of AI makes you realize artificial intelligence is already surrounding us. You know, it's so ubiquitous, just like plastic is so ubiquitous, that we almost don't see it anymore. So, you know, whether it's like using Siri and, I just called Siri, never mind. So, but, you know, using these different, you know, artificial intelligence you know, whether it's a chat bot, if you need help from Amazon, right? Have you ever tried to like figure out where your order is? You go on Amazon, you're talking to somebody or something, and sometimes now it's hard to tell the difference, you know, and the Turing test. I think about the Turing test about when computers become sentient and how to judge that. And so I think we're already in areas of that kind of vague overlap. That's one of the things is, first of all, we're surrounded by this already. But a second is that it comes in many different flavors, many different forms. And so whether you're talking about what Denise is interested in, which is these kind of like devices that can be embedded in commercial business, commercial buildings, or whether it's doing imagery analysis, tying things to street sweepers and looking for ways to judge the effectiveness of these very common tools. There's so many different types that if you truly want to go further with this, it serves your interest to understand the categories of work and the different types of machine learning, because depending on what your application is, what you hope to do with it, then you'll be moving to either towards, you know, kind of a convolutional neural network, or you'll be moving towards kind of like a different machine learning data cleanup things that we'll be going over in the afternoon. So there are different types of things you might wish to do. And so first of all, realizing that there's a wealth of artificial intelligence already in circulation, and that making your play at it, making your contribution to this or adopting those tools means to be as specific as you can be about what your objectives are, so that you're pulling the right tool for the job.
Yeah, thanks, Tony. I just want to do a time check. Are we up at noon, or how's this? Are we going to get pulled there? How are we going to?
We're breaking for lunch at 12:15, so we have about 15 more minutes left.
Okay, sure. So maybe what I could do is I'm going to go back to the slides, and I will give everybody a preview, and we can do a I think a little bit more here. Let me continue on with, and I think it's easier in the browser here because I have the other links here. So specific to litter abatement, I think there's a couple interesting projects out there that, and again, I think the general categories like we talked about, a lot, you know, it's based on imagery and the way we collect it, right? And so, you know, here's 3 demos, and I can also give one from our Casca of what we did at CalTrans. So I'm happy to do that as well. So again, give everybody a sense of, in general, what you could do with computer vision in this space. So the first one, I think there was a question, I guess one of the, let me see who it was. I believe it was Janet, I believe, that asked about sweepers. So here's an example, and I'm going to put this in the chat, but here's an example of some research that was done. I believe this one was out of Germany. And we also have a use case from Casca, which I can show in a minute, but they talk about actually using sweeper imagery and basically putting them on the street sweepers, right? And being able to collect that imagery. And in this case, they were usually, you're going to go after cigarette butts and try to discern them from leaves. And that was the focus of this study. But in this case, they actually had their result. So the same way you would have you would mount it on an edge device, and then it would stay ahead of it. Obviously, the challenge would be the objects are very small, but being able to detect that. And in this case, you can see very similar to what Tony had showed. You know, the way the models come back first is to actually identify the object in the image, so they could do that, and then after that, assign the score. And then you can see that they're trying to label what the accuracy is, and then actually do the count, and then from that try to identify, okay, how dirty or how many objects are in this area, and then that gets a sense of, again, what is the trash level within this area, and then again, this would be collect on an ongoing basis. And this is probably going to be a video. I don't think these are still images, so they're going to have to pick these up off a video. And then this is what these devices look like. And a lot of them are now becoming more, not quite consumer, but they're definitely available. And there's even vendors that'll specialize in these. So I know that for traffic operations, we've been talking to, you know, vendors about using cameras for traffic counts. So there are firms that are starting to specialize. And and that can both do both, right? So the camera actually picks up the imagery, can analyze it, and then send it back with these labels. So again, that's something that continually evolve in this space. It looks like though this, given that it's research, probably they just developed it. You know, this is probably just off the shelf. They mounted it and analyzed the imagery on their own. And in this case, there's actually a video. So if you want to, you know, check it out, they'll actually give an overview of the project. And then these were, looks like the accuracies that they came up with. And in this case, I think they probably did different weight, I guess, different models. But, you know, again, just trying to show their general accuracy as they work through it. And then these are probably, yeah, these are like the hardware specs across going to different devices that they used. But yeah, that's an overview. And then obviously they published their research. So that's the first link. The second one is using, again, very, you know, video systems. In this case, I'm going to put this link in the chat as well. But just another illustration of using AI in the space. You know, being able to detect, and in some cases, things such as recycling. So this is more object-based. So versus, you know, where it's like one sweeper, these are actual entire objects that, you know, you're trying to, you know, in some cases, you know, when you look at applying computer vision, it might be, okay, look at how many objects there are, but it could also say, tell me what type of object it is. And it's a little different classification problem. So there's a couple things going on, say in this photo, right? You have the first tiny object, you might do a count, and then from that, you might try to tell what it is. So in this case, this might be, it looks like maybe a sandy beach or something like that, where you would find some common everyday objects. And then that's where, again, these labeled data sets are being, how about a taxonomy would help, because then you can identify the objects being, you know, being identified. So again, they talk about, you know, CNNs, right? Convolutional neural net, they give a little flavor of that. These are some of the models that they use. And again, that's one of the nice things about computer vision is thanks to Microsoft and Google, they actually open source a lot of their technologies. So that in the project that we look at in the afternoon called Tensorflow, it actually then enables or uses some of these models, which are open source off the shelf. And we're going to get a little, you know, a little hands-on with it, but a lot of the consumer-facing apps like Google Cloud, like, you know, their Vision AI network, they actually run these models in the background anyway. So a lot of it, I guess, pun intended, converges, where a lot of the same models are kind of being used, or similar methodologies are being used across a number of these different applications. And so whether you're using Microsoft or Google, you know, the implementation is a little bit different, but the underlying methodology or model are very similar to each other. And in this case, yeah, this is more kind of another way of doing it. In this case, they're trying to identify more of the people versus objects, but this is in a way what you would get. And, you know, again, we've been showing these bounding boxes and the results. This is, again, another way if you're actually getting more hands-on with it, where you're actually trying to label an object. And then this is some of the work that we've done at CalTrans is actually label, like, what are the actual pieces of trash? And then in this case, they're actually trying to do both the object of what type it is. And then it looks like here, they're actually doing some rating. But when you actually initially train the models, what you would do is you have to give it a series of images and actually draw the bounding box and say, okay, this is a bottle, this is a can. And you have to do it a lot of times. That's why data labeling, getting clean data sets are very valuable because of that, is be able to, you know, because it's very labor intensive. So that said, they're starting to do some demos here, but you can see that there's, you know, labeling, it doesn't quite work because you have multiple objects. So again, that identify the object, multiples of them, and then be able to classify and say what they are. So a couple of problems going on beyond. So when we look at things like this, like at the very beginning here, like this looks easy, right? Like, oh, no big deal, we have a bunch of stuff. No, there's actual, like, you actually have to train a model, like, look for this specific type of object. We're going to train it that way. And then on the other hand, actually be able to discern, because you can see it picked up other objects as well. So these types of training and models can actually get, they are very sophisticated. But, you know, just want to give an overview of the problem when we look at imagery. Usually you have to first find it, or what we call identify or detect it. And then after that, be able to classify it. And also in some cases, segment the image, like actually identify, okay, in this particular image, be able to parse out like there's different types of objects. They're not just there's a bunch of random stuff. And then in which case, if you did that, you would get kind of mixed signals here, right? It wouldn't identify the right object. So when it says paper, it's only picking up a couple of these and not recognizing the other objects in the photo. So YOLO is another type of model. So again, different ways of doing image analysis. Again, there's more than one type of these models. Watson, again, this is kind of, again, based on their implementation, but these are those consumer-facing apps that I mentioned at the beginning. So in this case, IBM calls it Cloud Pack, but basically you're going to upload an image, and then you're going to it'll give you some suggested classes, and then you have some very basic toggles, and then you can analyze it and it will return, these results. Cloud Vision, I also mentioned, right? Very similar. So in this case, you're going to upload a photo, and I think in this case, they actually try to auto detect on you for you. So if you're dealing with objects, it's actually going to go and using Google AI with all the imagery they have out there, right? When you go to Google Images, how do they know what a tag, what it is, right? Well, they don't have people do it. They actually run the AI models, right? So anytime you're searching for images on Google, they're actually automated, or Facebook. I guess the joke, or not a joke, but the common, I guess, the thing is, I think like Facebook, they actually know what we all look like, and they actually can recognize everybody. They just don't do it on purpose. So like when you do tagging, they actually have people do it. But Facebook, like their AI is pretty much good enough to detect everybody based on our networks and our images. So that's the power of some of these networks, again, for good or for bad, right? There's that ethical use of it, right? But that's kind of what Google is doing, is that they're using their AI to actually look at these images and return to you some of these labels. And you can see it's actually pretty good here, where the packaged goods are picked up, and then they can actually pick up some of these jarred goods on the bottom. So again, this is what they call generalized AI, where you're sweeping across an image. You already have the taxonomy built. It's built on millions of images, and then it can actually, again, generalize really well versus, oh, I'm just going to look for fruit, right? Or I'm just going to look for packaged goods. This is actually going across the entire spectrum of objects. And then this is how you're actually able to classify objects or trash by type. Pretty powerful stuff here. Self-trained models. So again, you can actually start to customize quite a lot, whereas this is more the consumer-facing end. This is kind of a, again, if you don't want to code, don't want to get into it, Microsoft, Amazon, Google all have these services, and they tend to work reasonably well off the shelf. And then again, they're more for generalized pieces, generalized use cases. You can actually start to customize quite a lot. Here's a little bit of
trade-off. The trade-off, Walter, might be that it's not able to connect server to server, right? You're not using APIs. You're just kind of uploading into the model.
That is correct. However, all these services will have APIs available. So I actually have Google here available. So it's Vision AI, and they have the Vision API. And then same thing for Microsoft, where here's the consumer-facing, more of the consumer-facing side, but they also have a Vision API. So all these services have APIs, and I think this is Amazon recognition. You can go do both imagery and video, and I'm almost certain you can have an API on this one. But again, it has kind of both, where in the back end, it's going to run the same model. It's just how you want to consume it. If you want to get it back via API, which is very good for embedding into applications, versus if you actually want like just photo uploads, yeah, you would that's a good point, Tony, is actually then doing more of the consumer facing where you actually upload a photo. So kind of two different ways of doing it. So yeah, some results here. So I think we showed that in Tony's presentation, what the example outputs would be, different ways of looking at it, either through a chart, or this is pretty common, where you would basically have an image, and it might actually have a number of different labels that you give it, and then it's going to try to match it. And then in this case, probably not so great, right? This is a plastic bottle, but you're ending up with paper, or it's kind of doing a combination here. So again, not so great here in what we call a false positive. And then again, this is just initial research. So, again, feel free to kind of explore. I put the link in the chat. And then last one here, this is more of a hands-on, more of a tutorial, if you will. I'm gonna put this link in the chat as well. But this is using YOLO, which is one type of machine learning framework. OpenCV is kind of an open source version. Even though TensorFlow is publicly available, it still basically belongs to Google, whereas OpenCV is basically open computer vision. And it's basically for those that are, can code or want to code. You can actually use, OpenCV as an open source alternative. And in this case, this is getting a little bit more hands-on, probably a good segue for this afternoon. So yeah, they talk about object detection. So as I mentioned, right, finding the object in the image and then being able to run the analysis on top of it. So that's kind of part one. So yeah, this is, I think, one major thing is being able to identify, first find the object and then tell what it is. So again, two different problems. And then when they go together, it doesn't tend to work too well. You kind of have to solve for both, while you're doing these image analysis, right? So like, yeah, this is easy because they're all strawberries. But when you have other fruits in there, it gets to be problematic, right? So in this case, this one was easy because everything is, homogeneous, right? Consistent within the image. However, again, once you get into different types of objects, you need models that are able to handle it. So here they're getting a little bit more hands-on with the code, which we'll get into in this afternoon anyway. So won't go through it right now. They're going through all the steps of how to set up the model, but just to show that there's other alternatives out there. And again, common in computer vision and machine learning, a lot of things are open source. So if you actually want to see the full example, it's out on GitHub. So, again, pretty accessible for those that want to access it. But again, we've talked about more of the consumer facing or off the shelf solutions. So that said, I think that gets us to the afternoon portion. And then maybe we'll pause for any questions or comments as we're kind of coming up on time.
I have a quick question.
Sure.
Yeah, so for Tommy's presentation, that part, there's something about the precision and the recall on the tobacco waste. And for that one, how did you label the training data? It is the beginning of the presentation. Yeah, probably the middle of the presentation.
Yeah, let's go back up.
Yeah, we can go back to that. The best slide for that is
right. So this is fine too. So how did you label things like this? Is this manually labeled for every single picture?
Yeah. So for the tobacco product waste, we did. Well, actually, Lorenzo, you're here. Do you want to talk about the work that we did to label?
Sure, yeah. So what you're looking at in this image is a comparison of the ground truth in green and the detection in red. So the green ground truth, I believe, is this is the street sweeper data. So we got this from where did we get the street sweeper data from again, Tony?
From West Sacramento.
And they had already labeled the data set themselves. I'm not sure what process they took to label the data set, but the ground truth in green is what they labeled for this data set. So this is a comparison of what was automatically detected from a trained classifier and the manual, or I don't know if it's manual, but the label that was given to us for this data set. We had initial work with—
Yeah, can you go to slide 32, Walter? Can you go back just a couple slides, 32? So go ahead, Lorenzo.
Let's see. Yes, perfect. Yeah. So this is another example where there's a ground truth and there's a detection. Now, the ground truth in here, the green boxes were manually labeled by staff. And in this particular instance, I believe it was my colleague Pete Kahanen and his father actually labeled those by hand. And then the red is the trained classifiers detection. I don't think we have examples of the initial trash data set that we had crafted, but we do have an initial data set with, I forget, like 30,000 samples of data, I believe, or something. And that was, or maybe 3, I might be off by a factor of 10 on that. It's been a while, but that was labeled by an intern.
Yeah, there were 33,000 images. Yeah.
So 33, that's 1,000, that's basically like the training set, right?
For our initial trash detector, I believe for this Blacktop, we stuck with the Blacktop data. We didn't leverage the trash detection data for this particular classifier because we wanted it to just be for this Blacktop situation.
Yeah.
Okay, and those images, are they real world images, or that's like a experimental one?
Well, for the Blacktop, it is actually, as I mentioned, the Blacktop was seeded imagery. So we put the cigarette butts that you see there were placed there by us. So it's real world in the sense that it really was a Blacktop. It was a schoolyard or something. Again, we collected all the cigarette butts. We didn't just leave them there. But so it was a real ambient condition, but we did put the objects we were looking for in the image field so that we could know how many objects were truly out there. That's one thing. The other thing to point out, though, is that for the street sweeper imagery and the mobile imagery, those were not seeded. So we wanted to further extend the experiment, as it were, to see if we could use the same detector for applying it to more complex images.
Okay, so when you're training it, you actually mix both the experiment ones and the real world data together to do the training and the testing.
Yeah, we did the training.
Oh, they are separate. Yeah.
They're separate. Yes, we did the training using the seeded environment.
Okay.
But,
okay.
Lorenzo, correct me if I'm wrong, but we didn't do any retraining, did we? Using other imagery.
I believe we did integrate for the street sweeper. We segmented some of the data for testing and some of it for training. I think Ryland ended up doing a little of both, creating a model that leveraged the Blacktop and street sweeper, both train. So there was a training data set that had a subset of this labeled trash data that you're looking at. Well, the in slide 33, and as well as the Blacktop, and then we were testing on a subset that was left out of the training process.
Yeah, that makes sense.
Thank you.
Thanks, Ying. So Bob, you have your hand up.
Yeah, I wanted to make a comment going a little further on something you mentioned earlier, Tony. One of the areas of resistance we've run into with some of our public-facing clients is one city, for example, had put in red light cameras and got a huge backlash. So when they wanted to talk to us about building a web bot based on IBM Watson to answer questions about 1383, everybody had concerned, no, they'll think we're spying on them. And it's how you use the technology. It can be very invasive, like somebody trying to collect data from marketers, or you don't need to collect any of that. You're just providing information. So people confuse AI with invading their lives everywhere, every day. Those are just the people trying to leverage data to make money from it. As a government entity, we're trying to provide information and we don't need to collect much information. And so explaining that was able to alleviate a lot of the concerns. And Ying, it sounds like you and I should schedule a follow-up conversation to talk about the project we're working on and implementing some of this stuff. So I'm excited to do that. That's all I have before lunch. Thank you.
Yeah, Bob, yeah, we do need to break for lunch, but I just to respond quickly, that is really a very, very critical thing to bear in mind, is that people will come with their preconceived notions about artificial intelligence, and it's based on reality. It's not that they're mistaken. It is used a lot for surveillance, but in this case, that's not what we're doing. And we are, but it behooves us to think very carefully about how to avoid blending together, personal surveillance and any type of thing that we're doing here. So we want to make sure, as I mentioned before, that you're not surveilling people, that if you are using computer vision, that you're going out of your way to make clear that that's not your target here. So that's a very important thing to bear in mind. And also nomenclature. Think about the words you use. So we actually don't use the word drone to refer to our UAS. We do use unoccupied aerial systems. We don't even use the word unmanned aerial systems, which is kind of the standard term, because we didn't want it to be gendered. So think very carefully about the words you use. Think carefully about where the boundaries from observation, the boundaries of the analysis you're doing are going to be as you are making arguments to move forward with this. It is very, very important so that you're not blending together what you're doing with the type of surveillance that people worry about. Any other questions before we break for lunch? All right.
All right.
Well, sounds like we're going to break. So it is a kind of short lunch, but we will be coming back at 1 o'clock. So if you could return to this room. You can mute yourself or turn off your camera or whatever, but you can either stay in the room or come back to us at 1 o'clock. This is where the rubber hits the road. This is where Walter takes off the kid gloves and we dig into some of the data and really kind of get into the exciting hands-on stuff. So don't miss this. It's really fun. Oh, sorry. Actually, at 1 o'clock, you certainly don't want to miss it. This is where the Google Cloud team does their presentation. So don't miss that. That's in the main room. And then we will, after that, about 35 minutes later, rejoin things in our breakout session. So again, 1 o'clock, be in the main room for Walter to introduce the Google Cloud team. They'll be talking about their technologies, and then we'll be returning here at 1:35 to continue with some of the artificial intelligence hands-on work. All right. Well, thank you very much.
Yeah, thanks for coming in this morning, and hope to see you all in the afternoon.
Great, thank you.
And Tony, are we supposed to exit? Do we want to be in here, or do we want to go to the main room for?
I'll stay here for the time being in case anyone raises any questions.
Yeah,
and
same
then
here.
And you can move back to the main room.
Oh, okay, sure. I'll do that. Okay,
just because you might need to talk to the Google people. So.
Yeah, exactly. Okay, thank you. Appreciate it.
All right, thanks.
Yep.